just a matter of how many details I can cover, and I can stop, anytime. So let me just quickly remind you that what we did yesterday is we said that, okay, before the limit, we had a Gibbs measure Gn on configurations of spins which were finite vectors. So if you sample from this measure, you get these replicas sigma L. These were just vectors minus plus 1 with n coordinates. And then we said that the overlap, which in the SK model, the overlaps encode all the information. This was just the normalized scalar product between these two replicas. Okay. So then when we pass to the limit, so we define this formal way to pass to the limit. And in the limit, we had, instead of the Gibbs measure, so in the limit, we had this asymptotic Gibbs measure. Okay, which now lived on the space of functions. So when you sample replicas, these are just functions. So in any Hilbert space, but let's say in L2, just like we defined yesterday, on 0, 1 with Lebesgue measure. And we also saw that the overlaps in the limit will be just the scalar products between these functions. So these are just scalar products in L2 between the replicas. And so then we describe the Parisi ansatz for this asymptotic Gibbs measure, okay, which had two components. So there was a geometric component given by ultrametricity, and then there was a probabilistic component which describes the distribution of the weights in the Gibbs measure, and this was given by these Ruel probability cascades. Okay. And so today I will try to give some ideas behind the proof of ultrametricity. And well, I also wanted to show not just ideas in the proof that you can read, let's say, in the paper or in the book, but I want to explain where some of the main ideas came from. So in the end result, you don't really see them, but I think it's interesting to, in the talk to explain where these ideas came from. And so I'm going to start with this paper of Arguin and Aizenman just to review a little bit how things developed. So there was this paper of Arguin and Aizenman which introduced this idea of passing to the limit. But the main result in this paper that they proved that they showed that the so-called Aizenman-Contucci stochastic stability which I will describe a little bit later, implies ultrametricity under a technical condition when the overlap or the distances between points in the limit or the overlap takes finitely many values. Okay. So remember yesterday I said that when you have ultrametricity, you can always discretize. You can approximate by discretizing the overlap. But you
just review the. I have a couple of questions. Happening in the SK model. Do you just need L equal 1 and 2, or do I need more?
No. So in the SK model, what you need to describe in the limit is the Gibbs measure in the sense what kind of overlaps it generates. So if I sample again. a sample of arbitrary size, infinite sample. The question is, if you look at the array of their overlaps, what is the joint distribution of the whole array? Right. Okay. But equivalently, when you think of this picture, so if we can show ultrametricity, then I mean, we just need to show these two pieces, right?
So what does ultrametricity mean in terms of this R? I just go back and review that for a minute.
Okay, so ultrametricity here meant that. So okay, maybe let me put it here. So. Well, okay, in this context, it means that if you take any 3 points in the support of your Gibbs measure, the distances will satisfy the ultrametric inequality. But you can also, if you want, you can rewrite this in terms of the scalar products, because remember, they all live on the sphere. So you can express the distance in terms of scalar products. So in terms of scalar product, this would say that the scalar product between any two of them should be bigger than the minimum. So you kind of flip the inequality for the distance, and you can write it like this in terms of the scalar product. Okay? Okay. And so what I want to point out here that this is a very strong technical assumption. This is not something small that if you can prove ultrametricity in this discrete case, many people try, but there seems to be no way to extend this somehow to the general case. Because if you don't know ultrametricity in the general case, you cannot discretize. So logic doesn't go back like this. Now, motivated by this paper, about a year later, I proved a similar result where instead of this Aizenman-Contucci stochastic stability, I started with the Ghirlanda-Guerra identities. Which I will also describe in a second. And then you get the same result under the same assumption. Okay. And actually, a little bit later, a couple of years later, I found a very, very simple proof of this, like one-page proof under this technical assumption. But the general case turned out to be very different. So in 2011, I proved the general case without that technical assumption. And so that's what I want to describe today, okay? The ideas in the proof of that. So first of all, let me start by explaining what these Ghirlanda-Guerra identities and Aizenman-Contucci stochastic stability are. And for that, we'll need to go back to the original model. So these properties are obtained in the setting of the original model. And then when we pass to the limit, these properties also hold in the limit. But let's start with this system of finite size. And let me start with Ghirlanda-Guerra identities. Okay, so maybe let's erase this. So let me start by describing what these Ghirlanda-Guerra identities are. Okay, so it's very easy to state. So let me state them in the limit, actually, because then I can just write them precisely, not some approximate statement. So in the limit, they will be given by the following statement that if you sample several replicas from your asymptotic Gibbs measure, let's say n replicas, and then we will need to sample one more replica. So these are replicas from this asymptotic Gibbs measure. And then if we look at what the geometry of this sample of size n looks like. So let's look at the Gram matrix of scalar products. Okay, let me now switch the notation and write scalar product by the dot. So if you look at scalar products between these n replicas, so you have this n by n gram matrix, then what Ghirlanda-Guerra identities tell you is that the distribution, so conditionally on this, so if you fix what you see on the first n replicas, then conditionally on this, the distribution of a new overlap between a new replica, let's say one of these, let me fix the first one. So the overlap between first and a new replica, so conditionally on this n by n gram matrix, will be given by the following mixture, that with probability 1 over n, you simply sample it from unconditional distribution. So from the distribution of just any one entry, one overlap. But with probabilities 1 over n, you have to simply choose from one of the old values of the overlaps between this first replica and one of the other old replicas. Okay, so maybe if I write it out, so if you have this matrix here, n by n, and you fix this matrix, and then you say, how would you generate one more entry in the new column here? So what it says is with probability 1 over n, you just generate this independently, or with probability 1 over n, you pick one of these values that you see here. Okay.
The first one is 1 over n R1, 2, and then R1L.
Now, here is the distribution of R12. So you just sample it from the distribution independently of everything else. And the second is just a delta function delta function at this point. So this guy, you just pick, either you pick one of these values that you see here, or with remaining probability 1 over n, you simply generate independently from the distribution of this entry. But you notice the problem here is that it only gives this kind of marginal, but it doesn't tell you how to generate. Of course, you can generate any one of them by symmetry in the same fashion, but it doesn't tell you how to generate, let's say, 2 of them at the same time. So it only gives this kind of marginal. So that's just the statement of Ghirlanda-Guerra identities. And so let me explain where they are coming from. So it might look a little bit mysterious, but actually the idea behind is pretty simple. Of course, it's very nice, brilliant idea, but it's pretty simple. So the idea is the following, that let's consider the free, so we have the free energy. And let's write the free energy as the average of the random free energy. Okay, so the random free energy would be just what you get before you average with respect to the randomness. So log of the partition function, where the partition function is just the sum of these exponents. Okay. And then what we will use is just the two simple things. That first of all, both of these functions are obviously convex in the inverse temperature parameter. Okay, and another property is just by standard concentration, Gaussian concentration, this random free energy will be very close to its expected value. So you will have this concentration for the free energy. So for example, on average, the deviation between these two will be, it's something at most of order 1 over n, or 1 over square root of n, sorry. Okay. And then the idea is that if you have two convex functions which are very close to each other, then typically their derivatives will also be close to each other, right? So you can quantify this, that the convex function, you can control the derivatives. And so at least, of course, you can have some exceptional points, but at least on average over intervals, the derivatives will be close. And if you look what derivatives look like here, so the derivative of this random free energy, you just get 1 over n, 1 over a partition function, and derivative of the partition function, you just pull out this Hamiltonian from the exponent. Right? And so exponent divided by Zn, that's just your Gibbs measure. So you are averaging the Hamiltonian scale by n, and I will use this angle bracket notation for the Gibbs averages. So you just average scaled Hamiltonian with respect to the Gibbs average at this inverse temperature beta. And of course, the same thing for the non-random free energy. Okay, you just get expected value of this. Okay. So the convexity and concentration tells you that the Gibbs average is close to its expected value. And then you can do one more thing. You can look at the second derivative. And if you look at the second derivative of the free energy, well, the second derivative, okay, if you take a derivative here, you just, you have to remember there is a Hamiltonian sitting in the Gibbs measure. But if you compute this, this will be 1 over n, and then it will be the variance of the Hamiltonian with respect to the Gibbs measure. Squared like this. So, okay, you can divide by n, since we are looking at always normalized, and here you would multiply by n. But the point is that when you integrate the second derivative over some interval, you just end up with the values of the derivatives at the endpoints. But the first derivative is of finite order. So what this tells you that this integral over some interval of betas, let's say from 0, 1, will be small because of that additional factor n. It will be like of order 1 over n. And so what you get from this concentration and convexity, the Gibbs average is close to its expectation, but here the Hamiltonian is close to its Gibbs average. So if you put these two pieces of information together, you get that on average, the Hamiltonian itself will be close to a constant, to the expected value of the Gibbs average. Okay, and okay, let me just write absolute value here. So this will be small. Okay, this will go to 0 as n goes to infinity. So in other words, for a typical model, for a typical temperature, what you see here is that the Gibbs measure will concentrate on some constant level of the Hamiltonian when you look at it at the right scale. Right? That's the main piece of information. And where the Ghirlanda-Guerra identities come from, well, you simply what you do is you look at some test function. Let's say a function of the overlaps of n replicas. And you write, you test on this test function this fact that the Hamiltonian is concentrated. So this average will be approximately equal. So since this is basically like a constant, this will be just an average of f times the average of the Hamiltonian. Okay, and this approximate equality, it's on average. You have to still remember this is on average over intervals of beta. But now all you need to do is just integrate by parts, because and f is a function. Here I'm just looking only at overlaps. But you could also take functions of sigma more generally. It will also work. I'm focusing only on the Parisi ansatz, so I will look only at the overlaps now.
The overlap, you need the two couples, two copies of ensembles.
Right, so you're right. So what I'm going to do here, I will denote by the same notation the average over product Gibbs measure. So this function lives on n copies, and I will put the Hamiltonian on the first copy, the first replica. So you're right. This function is a function of n replicas, sigma 1 through sigma n, which depends only on their overlaps. Okay. So then if you integrate by parts, you have this Gaussian random variable sitting here and also in the definition of the Gibbs measure. So you can integrate by parts, and you can use the fact that the covariance, I'm reminding the covariance was n times the square of the overlap. When you integrate by parts, you will get
What is being integrated by parts?
You have to integrate this Gaussian random variable. So you take, for any fixed, you fixed here, you have a sum. So you just fix any particular value of the replica. You have a Gaussian times the Gibbs weight. So there are Gaussian variables in the Gibbs weight and here. And then you can integrate by parts. So
But the asymptotic expression you've got on the middle line there, that's just factorization. That doesn't require integration by parts?
no, here is just saying that this Hamiltonian is like a constant, so I just treat it as a constant.
Yeah. So, but now you're going to integrate by parts on which factor?
Okay, so integrating by parts, what I mean is you have the following formula. If you have some Gaussian and you have some function of other Gaussians, you can integrate by parts and you will get a sum of the covariance between G and GL times the derivative of f in that coordinate number L at that vector. So, right, that's all we'll do. And we will use for this G and GL this Gaussian and the Gaussian sitting in the definition of the Gibbs measure. Of course, not going to do all the computation, but in just one line, some computation of this type, what you'll get is the following, that when you integrate this function of the overlaps on n replicas, and there will pop up the new overlap with the new replica squared because of the covariance structure is the overlap squared. And then this will tell you that you will see exactly the prescription that we get from the Ghirlanda-Guerra identities, that with probability 1 over n, this is like independent copy. So the integral will become just the product of two integrals. n with probabilities 1 over n. This overlap simply will take value of one of the old overlaps. So that's what the Ghirlanda-Guerra, tells us, right? But of course, at this point, you just see it at the level of the second moment. That's one thing. And you also see it just on average over betas. You don't see it for any particular model. So there are a couple of things that you would like to do. You would like to be able to replace the square of the overlap by any power of the overlap, so that you get information not just about the second moment, but the distribution. And number two, you would like to have this statement not on average, okay? Somehow for any particular sequence of models that we're interested, not on some kind of average. So
you're averaging over beta, you're right.
I'm averaging over beta, which corresponds to saying, like, for a typical model. I'm changing model, right? I'm changing the beta, so I would like to avoid doing that. Okay, so that's what we would like to do. We would like to strengthen that idea and get a better version of it. Integration by parts on both sides, yeah, here and here.
But then the last term, this one that's coming on the left side.
So from this side, you will only get this term, and all the other terms on both sides will come from that side. Yes. Okay, so then the idea was that you simply use this idea as a perturbation of any model you like. So first of all, you will use as a perturbation Hamiltonian the mixed p-spin model. Okay, the mixed p-spin model. Because if you recall the covariance structure for the p-spin Hamiltonian, it was exactly the pth power of the overlap. So if I repeated the same computation with p-spin model, I would get the pth power instead of the square. Okay, that's one thing. And then what you do is you simply take any model you like, and then you add a perturbation term of this type. So of course, this guy is also of order n. So I will have to add some small factor in front of it to make it into a small perturbation term. Okay, so you change your model slightly. Whatever model you're interested in, you add a perturbation term. And then you can notice that when epsilon goes to 0, because this guy is of a smaller order, it will not affect free energy or ground state energy. Okay, so perturbation does not affect free energy. So that's actually a very powerful idea. There are other types of perturbation that induce some helpful information on the Gibbs measure. But here, then, if you do this, if you look at the proof how we obtain Ghirlanda-Guerra identities in that sense, the only thing we need is the concentration for the free energy. So the same method will work for any model you like, as long as you have some concentration for self-averaging for the free energy. And if you repeat the same idea, just working with one term at a time, taking derivatives and averaging only with respect to this one term, then you will get the Ghirlanda-Guerra type identities. Okay, first of all, for the pth power, because the covariance is of that type, okay. So you get this kind of statement on average over one parameter beta p. But once you have this on average over beta p, you can also average in all the other parameters. So you can say, okay, this is true on average over all beta p's. And then it's true for, if it's true on average, you can just pick, I mean, we are checking some kind of approximate equalities. Then you can simply pick one particular realization of beta p's, which of course can depend on n, because we are working here with the system of size n. But
missing something.
yes.
If I understood correctly, all you need is the self-averaging property of the free energy, right? That's
Right.
the sort of crucial property.
Right.
And now, but now you get overlaps, and so I didn't quite understand how overlaps appear.
Well, the overlaps appear when you take a derivative. You see here, when you have a new redefined Hamiltonian,
Yes.
I will simply do the same computation with one term, with this term number p.
Yes.
And so you end up with the concentration inequality, the concentration of the Hamiltonian for this guy.
Yes.
And when you integrate by parts, you will get exactly the overlaps coming out, because the covariance of this guy is a function of the overlaps. Right? So,
Probably, yes.
so see, when you integrate by parts, like over there, you have covariance coming out. And here the covariance is the function of the overlaps.
Okay.
So that's how the overlaps will come out. But my point is, what you get at the end is that for some perturbation, so there will be a choice of this, parameters beta p in this perturbation term, that you get all these approximate equalities for all p simultaneously, not on average over anything, but for some choice of the perturbation term. Okay? And so, and it works, it's very flexible. You can do this pretty much in any model you like, as long as you get some concentration. Okay?
But then you're going to ultimately let that epsilon go to 0, right?
Yeah, so you have to let epsilon, yeah, I forget to say one more thing, that first of all, epsilon must go to 0. That's important not to affect the free energy. But there is also another condition here, is that epsilon should not go to 0 too fast, because otherwise you can just set it equal to 0. So there is some kind of balance.
You need the epsilon. You need it to do what you want to do, right?
Right. So the epsilon shouldn't be too small. And the whole point here is that you will be, when you're averaging over beta, now because of this epsilon, you will be averaging over intervals of size epsilon. And so this approximation for the derivatives, the concentration inequality will play against this epsilon. And so the choice of the epsilon will depend on how close those two functions are, for what you get from the concentration inequality. So with this kind of concentration, you can check that you can take any epsilon 1 over n to some power for any power up to 1/4. Okay, but not faster than that. Yes?
Could you just say that if you look within the class models with parameters with infinite
Yes. Yeah.
By just convexity, almost every value of these parameters, the free energy is differentiable. Yeah. And then do the analysis for those special models, which are actually dense within the class of models. The free energy is continuous.
Yes, I have seen something like this. Yes, I don't want to make any comment because I don't remember the details. I have seen something like this in some papers, but this is my preferred way of things to do it because it doesn't matter for us what the perturbation is anyway. So the point is you can choose the perturbation that makes everything work. Okay, and then you don't have to do any other arguments. Okay, so.
It is going to be a problem that the derivative of the energy may have discontinuities.
You mean for the other arguments?
Yeah, in all this stuff. I mean, the free energy may
Right.
have some corners as a function of epsilon or betas, where it is not continuously differentiable, but apparently that doesn't matter.
No, here that doesn't matter because first we just look at things on average. We look at things on average over the intervals.
Yes.
And once you prove a statement on average, you just pick, one particular choice of parameters. Okay. So that's the Ghirlanda-Guerra identities. My main message here is that it's a very flexible tool. It's really not a property of any particular model, but it's a property that the mixed p-spin models can force on any model you like, just by using them as a perturbation. Now, let me now say a few words about, I guess I will not say much today also. So let me at least say about Aizenman-Contucci stochastic stability result. So the idea there is that, if you take some temperature and you change it slightly, let's say you redefine the temperature by adding a small, by changing it of order 1 over n, because we look at Gaussian Hamiltonians, of course, that's the same thing as to say that you are simply adding an independent copy of the same process with the factor t over square root of n, right? Where hn prime is just an independent copy. So the variances will add up to give you, that, right? So then this guy, let's put the square root of n inside the definition of this Hamiltonian. So let's call it little h n of sigma. And little h, it's a Gaussian process, but with covariance given. So remember, our covariance for the original Hamiltonian was of order n, had a factor n, but this will kill that. So you will just end up with, the square of the overlap or the pth power if it's a p-spin type Hamiltonian. But now this is, a Gaussian process with covariance of finite order. And adding this kind of term to your Hamiltonian will result in a change of density for the Gibbs measure, right? So the Gibbs measure will simply have this additional factor e to the t hn sigma. So this just defines a change of density proportional to this exponent here. Okay. And the idea is that such a small change of density should not change the Gibbs measure. When you look at Gibbs averages with respect to this new measure, they should be the same as for the original measure. Of course, this is not true automatically because what this change of temperature does, it introduces a change of density of some finite order. It's a non-trivial change of density, so it's not immediate that you get the same. But you can make this idea rigorous along the same lines as the Ghirlanda-Guerra identities. Okay? You can do this in the perturbation term, and there, when you average over temperatures, if you slightly change a temperature, it just means you average basically over the same interval, slightly different interval, and so you can choose a perturbation in such a way that this will work, that this type of change of density will not affect the Gibbs averages. So in the limit, let me formulate what this will give you in the limit. So in the limit, first of all, it's easier to state if we assume that the Gibbs measure is atomic. Okay? If it's not atomic, you have to write things in terms of integrals. But let's just pretend that the asymptotic Gibbs measure lives on some sequence of points with some random weights. And also, let's enumerate them just for certainty according to, so in the decreasing order of their weights, like this. So you have some asymptotic atomic Gibbs measure like this. And since we are interested in the distribution of the overlaps, let's simply look at this matrix of overlaps of all points in the support of this Gibbs measure. Okay. Then that change of density before the limit will result in a similar change of density in the limit. So let me denote this by GT. So you will have another Gibbs measure on the same points with the weights, let's call it PLT, where you simply make that change of density E, T, and you put some Gaussian process. And let me put a Gaussian process of the p-spin type. So let me call it GP, indexed by our points in the support of Gibbs measure. Okay. Where this GP is just like that. It's a Gaussian process with the covariance of the p-spin type. That means an overlap or scalar product between these points to the power p. Okay? And
your T perturbation is not is just it's just the usual. It's not the usual. It's just usual. It's not a p-spin type.
well, it's a p-spin type in this sense that the scalar, so the covariance matrix is the overlap to the power p. So I'm looking at, a general possibility to have this general covariance structure. And so what Aizenman and Contucci stochastic stability tells us that these two measures, you will not distinguish between them from the point of view of overlaps. If you sample from this measure according to these weights, or from the original measure according to these weights, and you look at the overlap, you will have the same distribution for the matrix. And you can write this down in the following way simply by saying that if you take the overlap matrix between the points in the support and you take the weights, the sequence of weights, it's the same thing in distribution after you make this change of density. But of course, what you need to do is to compare these two objects, you also have to rearrange these new weights in the decreasing order, because these weights were arranged in the decreasing order. So you simply have to resort things, and the notation typically uses like this. So if you apply the permutation that arranges this in the decreasing order, of course you have to also permute the matrix because the points are attached to the weights. But if you do that, you get the same object, right? So that's That's the Aizenman-Contucci stochastic stability. And what was really interesting is that in the setting of the Royal probability cascades, there was already a property like this, and even a more general one. It was a property discovered by Balthausen, Sneedman, in their famous paper on Balthausen-Sneedman coalescent. So I call it Balthausen-Sneedman invariance. So in the setting of RPC, where you have ultrametricity, you have that tree, you have weights generated by the Poisson point processes, it turns out you have very similar property, but additional information is included. Namely, you can also put here this Gaussian field that you use in the change of density. And after the change of density, what you need to do is simply shift this Gaussian field by some constant, t times constant that depends on p. And this constant just depends on the distribution of one overlap. Okay, so after you make this change of density and reorder everything, you basically end up with the same Gaussian field if you shift it by a constant. So you see there was this piece of information about Aizenman-Contucci stochastic stability. But there's this additional piece of information about the Gaussian field, the distribution of the Gaussian fields used in this change of density. And so it turns out the first observation was made by Talleyrand, who simply noticed that this Balthausen-Sneedman invariance, it automatically implies the Ghirlanda-Guerra identities in the setting of Royal probability cascades. We are in the different setting here, but you get the Ghirlanda-Guerra identities, and you get them very easily from this additional property. What you do is you simply take a function of overlaps of n replicas, and then you put this Gaussian field, let's say, on the first replica. On one hand, this is 0, because this Gaussian field is defined independently, conditionally on the Gibbs measure. So it's not present in the Gibbs average, so you can average it first. But on the other hand, this invariance property tells you that you can change the density in the Gibbs average, and you have to match this by just a shift in the Gaussian field. So here you have a shift, but you have now this change of density. So this Gaussian field also appears in the Gibbs measure. And then you do the same Gaussian integration by parts that I mentioned before. So you integrate by parts, and it gives you exactly Ghirlanda-Guerra identities. So this piece of information, it looks like Ghirlanda-Guerra identities. And so then I noticed that you can reverse this observation of Talleyrand. And so this is what I call unified stability property. Okay. So if you take Aizenman-Contucci and you take Ghirlanda-Guerra identities, you can write them together at the same time as this Balthausen-Sneedman invariance. So you can simply reverse this computation, and you can say, actually, this piece of information is just another way to encode Ghirlanda-Guerra identities. Okay. But of course, I have to emphasize, we are in two completely different settings. So here, we are working in the SK model where we don't know anything about the Gibbs measure yet. We just know Aizenman-Contucci and Ghirlanda-Guerra identities. And what I'm saying is you can write them together in this form, which formally will look just like the Balthausen-Sneedman invariance. Of course, here they prove it I mean, this comes out simply from the properties of Poisson point processes in the definition of RPC. So the proof is completely different. And so so what I've been trying to do for a while is to understand if we can use the unified stability property in a better way than we can use, these two stability properties separately. Is there some kind of information here that we are missing when we look at them at the Aizenman-Contucci and Ghirlanda-Guerra when we look at them separately? And so what I did is kind of a different calculation mimicking the Talagrand's calculation, but I looked sort of a Laplace transform on these Gaussian fields on all n replicas with some weights. Okay? So again, on the one hand, you can simply integrate these Gaussians inside first. So you get just e to the 1/2 the variance of that sum. So you just get lambda L prime. And the covariance, that's just the overlap to the power p, right? On the other hand, you can make this change of density if you match it by this shift of the fields. So here you can shift your fields. And you can make the change of density at the same time. Now here it's not really integration by parts. And I'm not going to say what I'm doing after this, but you can work. So if you don't give up right away, you can go through a few steps. And after a few steps, you end up with some new, I call it some new invariance property. And that invariance property was really the key to proving ultrametricity for the Gibbs measure in the general case. So the basic form of the invariance property is that you can take some functions, some bounded functions, and you can define, let's say, a function on some new replica and n old replicas just by the sum where you plug in the overlap between sigma and sigma 1 into the first function and so on. So it's just this combination, linear combination of arbitrary functions of the overlaps of new replica with the old ones. And then you can define FL in a similar way where you replace here a term number L. Instead of this function, you replace just by the average of that function number L on the overlap. And the invariance property is the following, that for any function of the overlaps, the distribution of the overlaps will not change under the following strange-looking change of density. So it will be a sum from 1 to n, FL of sigma L, sigma 1, sigma n. And in the denominator, you average exponent of this function here, f sigma 1, sigma n. But you average, so here you keep the replica sigma 1, sigma n fixed, and you average with respect to only sigma, so which I put this minus notation to say that that's the special average here to the power n. Okay, so you end up with this invariance property. So I tried to explain the idea of how this came about, but the truth is, after you discover this, you don't need to go through all of this. You don't actually need Aizenman-Contucci stochastic stability. There is now a very direct and simple proof using only Ghirlanda-Guerra identities. So you simply take this right-hand side, and you put a factor t in front of, in the exponent. And you put a factor t in this exponent also. Okay. Then what we want to show that phi of 0 is equal to phi of 1, right? Because at 0, these guys disappear. And when you start calculating derivatives, you will immediately, without any work, every time you compute the next derivative at 0, that looks exactly like Ghirlanda-Guerra identities that kill it. So all the derivatives are 0, and you also have a control of the derivatives, the proper control of the derivatives. So that just implies automatically that this function is a constant. Okay, so in the end, you only use Ghirlanda-Guerra identities to prove this property, even though, behind the scenes, the Aizenman-Contucci stochastic stability played important role in discovering this. Okay, so since
once you have these identities, what does that mean for you?
yes, so that's the rest of my talk, which I don't have time. But let me, okay, maybe in 1 minute I can say that what is something new and special about this, that after a little bit more work, you can strengthen these identities, and you can include information about the Gibbs weights of some neighborhoods. So with a little bit of work from here, what you can say that suppose you have a partition of your space on which the Gibbs measure is defined. And you want to look at the Gibbs weights of the elements of this partition. Now, this is not arbitrary partition. It has to depend, so the indicator that any point lives in one of these elements, it should be a function of only the overlaps between these old replicas and this new guy. So in other words, you can look at any partition which is defined in terms of the distances to your points, to your n replicas. Then, if you can reweight, yes?
So J is an index of all these subsets.
Right, you have some kind of partition of your Hilbert space where the Gibbs measure lives. The partition can be any partition as long as it expressed only in terms of the distances from the points. And then what you do is you can reweight these guys by some transformation where you would integrate over this set Bj with the weight given by exactly this guy here. Okay. Maybe I can give one example of this in a second, but then I will wrap up. Okay, so this is just a reweighting of your, of these weights, and then with a little bit of work, what you can do here, maybe I'm not going to rewrite this. You can say that you can also include the information about the weights, and here, if you put this reweighted weights of those elements of the partition, this still works. So this gives you an information about how the Gibbs measure, or the weight of the Gibbs measure behaves on some neighborhoods, that you are free to rescale it. For example, you can put, if you just look at let's say, a neighborhood of the last replica. So you can define the neighborhood. So all points where the overlap with the last replica is bigger than something. Right? On the sphere, this is just a neighborhood of this point. You can, and look at the complement as the second piece of the partition. So you just look at the, you're interested how the weight of some neighborhood behaves. And if you choose the functions here in the definition of this function f, you choose the first n minus 1 to be 0, while you choose the last one to be exactly the indicator that x is bigger than q. Okay. Then you will see here that when you are integrating over this neighborhood of the point, here you have just exponent t times the indicator that sigma n is bigger than q. So you're just integrating over that set, and you will see that this first weight just corresponds to exponentially reweighting the weight of this neighborhood. Okay. And the second, and outside, you're just reweighting, with the weight 1. So, okay. And so the whole idea is that you can take a neighborhood of a point, and you can assign much more weight to it, exponentially. You can put exponentially more weight by this reweighting. And the distribution will still be the same as before, as long as you match with some proper change of density. So it gives very strong information about the behavior of the Gibbs weights of neighborhood. And if you gave me 5 more minutes, I would explain the proof. But I guess I will stop here for now.